Let's hope we have audio this time. 1, 2, 3. Hopefully we have. So we had like the finite alphabet, and this is an example. I changed it a little bit, so you can see that this regression, there's a regression problem. You have like 40 levels for x, and then y can take any values in reals. And so what was the natural estimator here? So we want to estimate the conditional mean of y given x, right? Yeah, so for each level we go and take the average, and that would give us an estimator. So one point that I want to emphasize is that this setting is fairly general, and you might not appreciate it at first. But let's say I just want to point out that in classical statistics, what you would assume, not classical, but a lot of like papers that you see, including the ones that I wrote myself. So you'd see something like the non-parametric regression model is modeled like this. So y is f star xi plus some noise. And then usually you assume that the noise, these are IID, and either from Gaussian, it's zero mean and variance sigma squared, or at least from some distribution, but then you would assume, for example, that the mean is 0 and the variance is sigma squared. Okay, so this certainly falls within this general framework that we talked about. However, this is much more general in the sense that, so if you think about this situation, I can always, once I define this f star, I can always write, let's say, my samples, I get y I is f star, let's say xi, plus some residual. Okay, I can write a residual, which is just basically defined as yi minus f star xi. The thing is, this guy is not necessarily assumed to be independent of x anymore. Okay, so this could depend on xi. By definition, this is just a residual. The thing is that this is, because of the properties of conditional expectation, you can show that this is going to be uncorrelated with xi. So with the expectation of, this is like the conditional mean if you take the expectation under xi. So what is the conditional mean of this? Yeah, why? Yeah, so you get the conditional mean of yi given xi, which is f star xi, and this comes out of the expectation. So this is 0. And so if I take another expectation by smoothing, the marginal expectation is also 0. So these are 0 mean. And then you can also show that the expectation of, if I do this times xi, let's say, conditional on xi, right? I can pull xi out, right? And then this is 0. So this is 0, and then you get that expectation of epsilon xi is 0 by applying the smoothing. So take another expectation. So because it's 0 mean, and the second holds, this shows that epsilon and xi are uncorrelated, but they might not be independent. Okay, and in particular, the thing interesting is that the variance of this could depend on xi, and that we saw. So this is the variance of, so if you remember, we said variance of, these are IID, so this is, we define as sigma x. So we allow this to depend on x. In general, it has to depend on x. And so this is called heteroscedasticity, something like that. So the variance of the observations could depend on the covariate, okay? And that would be the variance of this, conditional variance of this given xi. And so there is some sort of an average variance, but it's just worth noting that this is very different than this setting. And this shows, for example, here, I changed the example. You can imagine that the conditional variance, so how do we like visualize the conditional variance of y given x? Where is it high, where is it low? So basically we go at each level, you look at, this is the conditional distribution of y given that particular x, right? So here we have high conditional variance. Here we have low conditional variance. So the result that I'm going to talk about just covers this. And in fact, Stone's theorem that if we manage to prove allows the conditional variance to be unbounded in the sense that it doesn't have to be bounded in a certain like bound. So you could like, it's not like infinite, but as you vary x, it could vary widely. Okay. So that is useful to remember. So there are kind of results that go beyond this classical setting of homoscedastic, I believe, if I'm pronouncing it correctly. The case where the noises are all having the same variance and they're independent of the covariance. If they're independent of this, then basically we can condition on xi and just treat them as constant. Basically, this is traditionally what has been done. Just point that out. Okay. Questions about this? Just some comments about generality, the setup. So the estimator that we did was basically if you look at this set, this is the set of all let's say xi's that are equal to a particular x. Let's say I focused on estimating the regression function at a particular x. So that's the part that I want to do it. So for this x is going to be just a number, and that would be the average of these coordinates. And so you would get this estimator, and you could imagine this has to be some sort of an optimal estimator. One issue with this is we're not borrowing information from the other levels, okay? But if I don't know anything about the distribution, maybe I shouldn't borrow. So if you want to borrow, you have to impose some assumptions. The question is that do we have to borrow or not? I'm going to leave it to you to think about. But basically, at this x, we just care about these points. Okay? At this x, we care about these points. The behavior, the function here has nothing to do with the behavior here, for example. Okay. But there is one point in that I could care about. This is another point that I want to maybe mention. You might care about the performance individually at this point, or you might care about the aggregate performance across all x's. So that would change things a little bit. If my loss just cares about this part, if I perform badly here, it doesn't matter. I might just change my estimator to do better here. But if I care about the average behavior, then maybe I need an estimator that works for every x. And so in this finite setting, it doesn't matter, as I mentioned. So if you define this estimator, which is just averaging yi's over this set ix, which is all the points that are equal to x, then what we showed is that this is universally consistent for f star in the sense that point-wise it converges in probability, and then you can translate it into uniform convergence. So uniformly converges. I'm going to use this notation f hat n minus f star infinity. L infinity, this is just the supremum or maximum over x of these guys. This turns out to also converge in probability to 0. And then maybe for your own understanding, you can show that the L2 also converges. So in L2, we also converge. The L2 here is going to be just summation. I'm going to write this px. Yeah, let's do px. Okay, I'm going to do maybe mu x. Let's do px. F hat nx minus f star x squared x and x. Again, because this is finite, you can show that this converges to 0, again, in probability. And here P of x is just the marginal distribution of x, which is, in this case, like a probability mass function. Okay, so everything here works out or reduces to this point-wise convergence, if you want. So we are consistent point-wise and also infinity, L2, LR, whatever you want. So everything sort of is fine. And then the proof, if you go, it has elements of the general proof which is to basically control the conditional mean and the conditional variance. Okay, so if you recall, I don't have the proof here, but I'll switch to the proof. We use the Chebyshev and then control the conditional variance and the conditional expectation of the estimator, and then remove the conditioning by smoothing. Okay, so any questions so far? So I want to extend these ideas. There's a very general theorem, which is called the Stone's theorem, that I'm going to hope to maybe talk about in this lecture and the next, that just extends this to the very general setting. Just basically answers the question almost completely. The question is that, let's say if I remove this assumption that x is finite, should I modify this estimator? So suppose now that x's are continuous. Okay, it doesn't make sense to go and fix a particular x and then try to see, like, average the things that are just, so this set, for example, if x's are continuous, what do you think would happen to this set? If I fix x, what would happen? Right? Yeah, usually, like with probability 1, if the distribution is continuous, at least, there's no point mass. This would be empty for all x. Okay, so there's no point in trying to do this. And also, like, computationally, you can imagine, I can't do it. We'll see. We can, like, theoretically do it in a sense. We'll see. But, like, in practice, you don't want to do it you can't do it for all reals. Okay, so what is the solution? So what should be? Balls, yeah, exactly. So what you can do is that at each x, if I want to estimate the function, I'll put a little ball here, and then it will capture a bunch of points, and then average the y's for the x's that lie in that ball, right? So so imagine this is actually continuous. I don't have the continuous version, but if I want to estimate at this point, I put a little ball, which is in this case an interval. Okay, so this interval, all the points whose x's are in this interval, I'm gonna go here, and then I'm gonna average the y's. Okay, I'm gonna average the y's for so the y levels here, and then I get a number that I would declare that to be my estimate at point x. Okay, so this is a particular form of an estimator, which is called, anyone knows what it's called? Yeah, this is not a Watson kernel estimator. So this is, for example, this guy. This is an example of this guy where if I take phi to be, so phi here is like a rescaled kernel. So if I have a kernel function, that's exactly this. This is the L2 ball. So if you do it like in the plane, let's say RD, so the input domain X is R2. This kernel is the indicator of this ball, the unit L2 ball. Okay, and so it's going to be 1 over this area. It's 1 over this area and 0 elsewhere, right? And then when I form this, there's this edge which is called bandwidth of the kernel. When I do this, what would happen if I do this, like dilation or scaling? What would the function be? So this is, let's say, 1 here, and then the radius of this is 1. How about this is kx. How about like kx divided by h, 1 over h? It's hard to actually plot, but so you can imagine that it's just 1 here, comes out of the board, so the z-axis, and then 0 elsewhere. The other one would be, if I do this, you can imagine I have to do x over h here, and then I can move h to the other side. So it's just going to be 1 over h over a smaller ball. Let's say h is big. So it's going to be 1 over h here and then 0 elsewhere. Okay, so you can control the neighborhood basically. Okay, and then when I put it here, you just translate it to point xi, right? So that would be like, this is phi of x basically. and then I translate it to point xi, maybe here. And so this is going to be 1 over h here, and then 0 elsewhere. And so it captures basically every point that is in this little ball here. So when I put it here, it's just going to be 1 over h, the weight 1 over h for every, sorry, I'm going to put, sorry, this is going to be, what do you mean by h?
If from the definition of finite, then we're taking the over x norm should be x, norm x less than equals h.
Yes, that's right. So did I have any? Oh yeah, no, yeah, right. The radius is h, right? You're right. Sorry, I made a mistake. Yeah, so this, if I made it, so h, so when h is, yeah, the radius is h, so h small is better. So h is controlling the neighbor, radius of the neighbor, okay? Yeah, what you want to do is not, so let's say I translate it to point, basically, let's say phi of, I want to do like dot x. So dot x means this is, x is fixed. This is now a function of this point. This is going to be centered at x. So now captures anything which is in a ball of radius h around x. Okay. So if you just write it down, so this would look like summation I from, not I from, yeah, so let's say summation I in h times, or, okay, I'm going to write this like this. A ball of radius h centered at x, and then 1 over h everywhere here, which I can put out, and then yi, and then divided by 1 over h summation, the same thing, right? I in b of x h, and then just 1 or 1 over h, okay? So it's just, this is 1 over h indicator. Another way of writing is like 1 over h indicator xi minus x is less than or equal to h, right? So that's what I mean. So xi belongs to the ball of radius h centered at x. If sorry, x, not I, yeah. Xi. Correct it a little bit. Xi, here is xi. Right. So I'm going to average. Yeah, bad notation. This is semicolon. So let's say I just avoid x and h. So this is a ball of radius x and h. I'm going to do better. 1 over h here, yi, and then 1 over h here. Okay. And if you simplify in the end, what should we get? H here. If you simplify, 1 over h goes away, so you get xi in b xhi divided by just the cardinality of this set, the set of all I such that xi belongs to bxh. Okay, how many points that are in that ball? So this is just basically forming an average, right? So you're averaging over all the xi's that are in this ball, and then dividing by how many they are. So it's just the average of the responses. Does that make sense? So the notation is like a little bit more complicated than what it is. It's just what you mentioned. So that's a particular example. And then you can imagine you can change this kernel. This is called Nadaria-Watson kernel estimate. This could be, this is just cut off everything at radius h, but you can sort of taper down, right? So you could imagine instead of this, you could have a Gaussian here. If this is a Gaussian, a multivariate Gaussian, then it would be like putting a lot of weights here, and then the weight sort of shrinks as you go down. So you basically average everything but the things that are away from your point X are gonna, the responses are gonna weigh less. Okay. Sounds good. So that's a particular class of estimators. There is another class which is slightly simpler, but they're related. These are partitioning estimators. So instead of putting in it, yeah, go ahead.
Might be a bit of a pointless question, but what's the reason of putting like the 1 over each of the like each function? Doesn't it just cancel out, right?
You're right. So you could just remove it. Forgot why I did this, but yeah. So you're right. So in this case, this is gonna go away. Traditionally, so there are like let's say kernel density estimates. So if I want to estimate the density of the points, I would sort of let's say I could do something like this. That's the that's a function which is an estimator for the density of the x, and then 1 over h makes sense. Okay, because you want the integration to like wanted to integrate to 1. Let's say if x if this integrates to 1, then this also integrates to 1, and then this is like 1 over n. Okay, so 1 over n this. Yeah, so that's basically. But it's a great point. I think some books don't put 1 over h there probably. Yeah, but that's a good point. Okay, another question, Eddie? Yeah. Good, okay. So the partitioning estimator, okay, so maybe talk about k-nearest neighbors. So k-nearest neighbor is a very similar idea. So what is it? So anyone recall? Probably most of you know what k-nearest neighbors are. So instead of putting like a ball, I'm just gonna go and find the k nearest neighbors, okay? And then average over those instead of everything that's in the ball. We're just gonna average. I haven't written it, but you can write it. So you can, basically you change the definition of neighborhood. The neighborhood, instead of being defined by this kernel, it's defined by your data itself. Okay, so it's the idea is the local averaging. Partitioning estimators are really simple. What it does is something like, I have a plot here. So this is the two-dimensional space. This is the distribution of x. I'm just going to partition this space, let's say, into whatever cells I want. This is a cubic partition, or like rectangular partition, square partition, whatever you want to call it. Just regular partition. And I'm going to go into each cell and then average. So the points that fall within this cell, I'm going to average the y's for these points. Okay. So here, for example, the cells are empty. We can arbitrarily define the estimator. That's one of the issues that we had. The average sort of doesn't make sense, but I mean, in here, it's just arbitrary. There's no data. But here, I have a bunch of data. I'm going to go average the y's for these, average the y's for these, and so on. This is simpler because it's just going to be block constant. You can imagine, right? So every x that's in this partition gets the same value of y. So you're if I'm not wrong, correct me if I'm wrong, but the function that you output is block constant, or piecewise constant. Okay, piecewise constants over these partitions. Does that make sense? So this is the first one I want to maybe analyze because it's the simplest one. So you can imagine there are some tensions going on. So maybe just mention a few, like what are the considerations? So how should we choose the partition here? So you imagine, for example, is the estimate here better or the estimate here would be better? The estimate of the regression, yeah. Yeah, so the one that gets more points is going to have more like accurate estimate. This is going to be less accurate. This is less accurate. So you have this issue that you want to get more points. So maybe what I would want to do is, like, instead of partitioning like this, I want to partition like this. So double the size of the partition. Okay. If I do that, then instead of estimating things here by just a few points, I'm going to estimate things here and here, and here, and here by all these points. So I get a better estimate in terms of the variance. But what is wrong with that? So if I increase the side length, like double the side length, what would I lose? The accuracy, yeah. So you would lose, basically when I translate it, you would introduce bias because now everything here in this big region is going to be estimated by a constant. If the function fluctuates a lot here, you just lose that. So there's a tension between the bias and variance. So if I refine it further, I can just subdivide here more, right? And you can see if I subdivide, I tend to become more, it's hard to say accurate, but I reduce the bias because now all the points that are, let's say, in this little tiny piece are going to like define what the value of function is here. But I'm going to also lose, like I'm going to increase the variance. Okay, so the fewer the points get in there, the larger the variance. So there's this tension between the bias and variance that hopefully we'll see, and so that defines the behavior of all these estimators. So you want to balance out the bias and the variance, and there is like a wide range that allows for consistency. But if you want to be optimal, what is the optimal right choice? And then you can imagine for partitioning, it might be that this is not the best way to partition for this particular data, right? Maybe if I align to these axes, I would do much better, right? I could maybe like do like rectangular, let's say align myself to this, have rectangles that are like parallel to this, and not too many, let's say boxes in this direction, but more boxes in this direction. I might sort of adapt to. So this is not adaptive, for example. So the other estimators like decision trees would, or like regression trees, would sort of adapt in a sense. So this is also a partitioning estimator. You can write it like this, not like this actually, like the version which I'm going to introduce. But the partitions are also defined by the response as well. Okay, so the adaptation that I mentioned is adapting to the distribution of X. I'm not talking about Y, but decision trees are a little bit more clever. They also consider Y. Maybe this is X, but maybe Y is really actually very variable in this direction, not much variable in this direction. So I might not want to partition that much in that direction, but more in this direction. So it's like a supervised partitioning that you provide. So it gets quite complicated. So if you can imagine, this is simple, it might be consistent. So the advantage of the result I'm saying is very general, like I'm going to talk about it works, but the disadvantage is that all these refined points are like gets lost. But as you analyze it, you get a feel for what are the different terms that you have to control, and then maybe you can improve the analysis later. The question so far? So there's another class which is called local polynomial smoothing estimators. So so you can like couple this with something like that, like this kernel idea or the partitioning idea. Let's say in this case, if I want to couple this with that, instead of averaging, I might try to fit a higher degree polynomial here. So instead of like averaging, which is constant, fitting a constant, I would try to fit like a linear function or a quadratic function. And you can also imagine coupling that with the kernel idea. So you would you would fit a polynomial, but you weight your data points with that kernel. So you mention it like this. So you would solve something like minimize argument summation yi, let's say. The very basic idea is like I fit a linear function, so the beta transpose xi, let's say minus beta naught, which is the intercept, squared, and then times phi, let's say x minus xi. This is capturing my weights. Okay, so this gives me f hat and x. So I fix x. For a fixed x, you're going to solve this over. Well, actually, this is not going to give me. It's going to give me beta hat. Let's say beta hat 0 if you want. Argument over beta and beta 0. Beta in RD. Beta naught in R. Right, and then my estimator would be I should want to be careful, beta hat x and beta hat naught x. It's going to be argument that f hat and x would be just beta hat x transpose x plus beta hat naught x. Okay, so for each fixed x, I'm going to solve this. I'm going to get a beta hat and beta naught that would depend on that x. For a different x, I'm going to get a different thing. So you can imagine this is hard to implement in practice unless you care about the particular point, because you have to go for every point and do this. But then you'd get an estimate. So the idea is like in this simple case, for example, I would go in this neighborhood and I'm going to fit a line here. Okay, that would be my estimate. So if you want to be like use the partitioning idea, you could just fit one line in every partition. That would, but there's no guarantee that you'd get like a continuous function. But the local polynomial smoothing is that for this particular point, I'm going to just fit this line, and then the value of this line at this point would be my estimate. For something here, like just the neighbor, I'm going to change the neighborhood here. I'm going to fit a different line, but then the center point value would be my estimate for that. So it just smoothly varies. So these lines would vary like very smoothly, and then the center point would follow a path that would be your local polynomial smoothing. So it's just a lot of work for getting an estimate at a single point. And then if I move to another point, you have to redo everything from scratch. But these have a lot of interesting properties. In particular, they're sort of optimal for if you assume the regression function is smooth in a sense. And we might talk about that. Okay, sounds good. And there are like other things that we can talk about, or you guys maybe can talk about. So if you like have seen like the literature in machine learning and deep learning, there is sort of this idea of local averaging sort of rediscovered in the form of like an attention mechanism. So if you want to like follow that sort of talk about that or connect it with these ideas in your projects, it would be interesting. I might talk about that at some point as well. But basically, the idea of focusing on a particular part of the data that's relevant to the current, like, let's say, test point. So this is like an image. I'm not going to care about all the other images. I'm just going to care about the images that are close to this in a sense, maybe this in this particular region I have. But then I think there are more adaptations that happen. So you might try to, like in the attention ideas, you might try to adapt this as well. So put some parameters on this phi and then try to learn those parameters as well. It's like a level, like upgrade of this mechanism, which is a little bit more basic. Okay, so you could try to locally adapt. In the adaptation, you can sort of learn from the data. Okay, questions? So what else we should talk about? Okay, so there's another thing I want to talk about. Okay, so all these estimators can be written in a simple form, which is like this. So a general local averaging estimator is an estimator which can be written like this for a bunch of weights or a sequence of weights. So the n here just stands for the fact that I have a sample size n. At some point, you might drop this first n for simplicity, but I have like n the second index, so indices indices into like the weights associated with each data point. Okay, and so I have to specify these, and these weights could be random, dependent on the training data. And for example, the partitioning estimator has this particular set of weights where if I have, so I might write the partition like this: A n1, A n2, A n n. So the thing is that I would like to change the partition as the sample size changes. Okay, so if I get more samples, I might try to refine the partition, because now I can keep the same like proportion of the points in the partition by shrinking it if I get twice as many points maybe. Okay, so you want to let the partition grow or shrink depending on sample size. So that's where the n is. But okay, this is not n necessarily. So this could go on, like there's no need to like have exactly n. So this is like a partition. This notation is from that book, DFT, distribution free regression. So this is like the component of partition. The partition that contains x. So for example, a n x would be a n j if x belongs to a n j. Okay, so you can mentally remove the n here, just bothersome. Okay, it's just for example, for this x, ax would be this. For this x, it would be this. Okay, it's just a set function. So you specify x if outputs a set. Okay, that's like ax for this x. What happened here? Okay, you're not playing any music. Okay, so so if you imagine, this is the base, is that every point that's in that same partition, like cell, let's call this the cell, the component or the cell. Every point that's in the same cell as x gets a weight of 1, and then I divide by the total number. So you basically turn it into the average. And then you can easily write this for the kernel estimate. And for decision trees, it's also like this, or like regression trees. There is a key difference though. Anyone knows what decision trees or regression trees are? Right. So what is the difference, for example? Like the format is like this, but there's something about the weights that's different from this or the kernel estimate. So these weights for these estimators that I mentioned, they only depend on the x's. Okay, they don't depend on y. And the result that I'm going to talk about is about this case. Okay, for the decision trees or regression trees, these weights are determined both by the training y and the training x. Okay, so you split, you define these regions based on like the purity of y, and so it's just both a function of xi's and xn's and yn. So the analysis would be more tricky. Okay, so we were going to focus on the case where these are random, but only dependent on xn, which is just the collection of all x's that I get in the train. So these are some of the notations I'm going to use. Xn is x1 up to xn. And I'm going to also use dn because people use it. It's like the collection of all the training data. Okay. X2, y2. Okay, so is this clear? So we would like to have a general result about this type of estimator. Okay, a local averaging estimator where the weights are determined by the x's in the training. Okay, this would include the partitioning estimator, k-nearest neighbors, Nadarya-Watson kernel estimates, and whatnot, but exclude, for example, decision trees. And how about the local polynomial smoothing? Do you think you would exclude this, or I think you would also exclude this one because this also takes into account the value. Actually, no, is it? The weights are. Yeah, I believe if you do it, you're right. So I believe this is still like valid because let's say for this case, the solution would be a linear function of yi's. Okay, and then the weights would depend on the x's. Okay, so the dependence on y would be, I believe, but check. Okay, it's worth checking whether it follows this or not. Let me just find somewhere to plug in. So finally, let's talk about the Stone's theorem. So this is a paper that came out in 1977. And you can see he was at UCLA, so we have to talk about this probably here. It's a very interesting paper. I encourage you to have a look. It's very, so it's not often that you like write a paper and then 45 years ago, someone can read it and understand easily. So it's like the same. So very clearly written, and you can see it's just exactly the problem that we're looking at. So let x and y be a pair of random variables in RD given a random sample. This is the training from the distribution. The conditional distribution of y given x can be estimated non-parametrically. So actually, so it's just in the abstract, he also provides a non-parametric estimation of the conditional distribution. You can see exactly. These are the weights, and this is just the indicator yi belongs to A. So this is the probability of a y in A given x, and so if you care about a particular event, so you can estimate the conditional distribution easily by this averaging. So let's say if I want to estimate this, my estimate would be summation, say approximately summation I from 1 to n. Relatively small. Think that this x and indicator. Instead of just averaging yi's, I'm going to average these indicators of yi's and A, so that gives me an estimate of the probability, because this probability is just an average. This is just expectation. So you know that the conditional, because we know how to estimate the conditional expectations, the probability, conditional probability is just the conditional expectation. So this is just the local averaging for this function. Okay, so I'm just applying it here, and instead of yi basically here, I'm just plugging in. So it's just like a z. So you have zi's here. So this is nice. One of the difficulties is that there are many a's. So this is like probability measure. You have to control over all a's, which is if you want to like estimate the entire conditional probability, it's a little bit more tricky. So we focus on the estimate, it's like the function, the non-parametric regression, because at least it's a function. A function usually is slightly, hopefully less, like the space is smaller in a sense than the space of probability measures. But if you care about a single point, a single event, then this is a perfect estimator. So all the things that we talk about sort of works here as well. But then sort of he goes on. These are the weights again, so you can see that they're dependent on the x. This is so I'm writing here for a fixed x, but at some point I'm going to switch also to a random x. That would be a test x. Okay, and then so this would depend on both the training data x1 up to xn and also the test point x. So okay, so that's, we can read the introduction, and then here's his theorem. And I'm going to format it a little bit, change some of the conditions. So, but it's very similar to what we're going to talk about. Okay, so you can go back to this paper and check some of the assumptions are slightly different, but most of the assumptions are the same. So assume that we have a sequence of weights to satisfy the following conditions. There's a constant C, there's a constant D, such that these 5 conditions hold. Okay, then for any distribution P with finite second moments for Y, we have this sort of consistency. Okay, so F hat N is this averaging estimator, right? And then F star is just the conditional expectation or the regression function. Okay, so there are a couple of things to unpack here. One thing is the meaning of this. I wrote it in a little bit of a compact form, but this is basically we're going to talk about what this means. Okay, this is like related to the performance measures, but it's a form of consistency, L2 consistency. So what are these conditions? Let me talk about the conditions first. This one is, so the result is fairly general. So the weights need not even be non-negative. So you could have negative weights. And you can see in some of the conditions, the absolute value appears. In one, basically it doesn't. So this is a technical condition. This sort of says that if I plug F here and then take the expectation, I reproduce the expectation up to a constant. This is not hard to achieve. And hopefully if you go through the proof, you can see that this is not needed. Let's say if the original F is continuous and the space is compact. Okay, so this condition is just used to reduce the problem to the case where the regression function is continuous with compact support. So if, let's say if your domain is the 0 to 1, like we're on the plane, right, on the cube. So I'm going to restrict myself to this, all the functions that are living here, and then the continuous function, the regression function is like that. I don't need this condition. However, the universality sort of allows you to have like wildly different, as long as they're in L2, there could be discontinuities and things like that. So this takes care of it easily. And hopefully you'll see in the proof. So that's not really an informative condition. This condition just says that if I sum these weights, yeah, in absolute value, they're bounded. And almost surely. And this is almost always the case for us. And in fact, usually for us, this is just 1. So if you go back to this, these weights, they're non-negative. And if I sum them, if this cell is non-empty, then the sum would be 1. If the cell is empty, I can define it however I want. Let's say I define it to be 0. Okay, so this is going to be less than or equal to 1, the sum always. Okay, that's the tricky part, which is the empty case. So for us, this is going to be usually less than or equal to 1, non-negative. These are called sub-probability weights. So if they're equal to 1, the sum is probability weights. If they're less than or equal to 1, they're sub-probability. So this is also a mild regularity condition. These 3 conditions are then the things that actually control the bias variance trade-off. Okay, so we'll see that these 2 control the bias. This controls the variance. Okay, so if these 2 go to 0, and these 2 hold, then the bias goes to 0. If this goes to 0, then the variance goes to 0, and then together this entire thing goes to 0. This is again easy to achieve if they're non-negative and sum to 1. This is automatically satisfied. But for this case, usually you have to worry about. Let's say for the partitioning one, you have to worry about the case where there is nothing here. So there is a possibility that this is not sum to 1, just 0. So you have to rule out that possibility. Otherwise, it's going to be exactly 1. So verifying it is just a simple exercise in probability for the partitioning. So I would say this is also quite simple to achieve. These are the 2 main things. Okay, so this is saying locally, for every A, basically, the effect of the weights, let's say far away from your current point goes away. Okay, that's hopefully saying if you look at all the data points that are outside the ball of radius A, centered at X, and you sum all the weights, the sum eventually, as n goes to infinity, that sum goes away. So like the long range influence dies down, which is like intuitively should be the case, and you'll see in the proof how this comes in. And this is also easy to see from the proof that this is related to the variance. So the variance, if the variance has to go to 0, this has to go to 0, and then there's a tension between these two. So you try to satisfy this, then you try to violate this. So these are the two main key conditions. Okay, so is this sort of clear? The idea. So it's a little technical, but the point is, once you go through the proof, you can see exactly what happens here. So let me talk to you a little bit about maybe what we mean by this condition. This is related to how we measure the performance, and so it depends on whether the problem is regression or classification. Things are a little bit different, but let me just maybe like take a detour, talk a little bit about this. So in the warm-up example, all the measures basically were similar. Okay, so because the space was finite, here things are a little bit more tricky because I'm dealing with a function, so I can look at. So this is a random function dependent on the training data, but I'm evaluating it at a particular x. So sometimes if I want to be more explicit, I write something like this. This is now a decision rule. This is a deterministic quantity that takes x and the training and outputs a number. When I hide this, this is now a random variable. Okay, so I just want to maybe point this out because things get a little bit confusing. So you can think of things in terms of decision theory. If you're thinking 200B, you specify decision rule, which is deterministic procedure, how to get from x and the training to an estimator. That's a deterministic thing, unless you're looking at randomized estimators, which even this is not deterministic, then you'd also put it like an external source of randomness. So it's the point and take the training and output an estimator. But let's worry about just non-deterministic. This is deterministic estimator. So when I write f hat n, sometimes I mean this deterministic decision rule, sometimes I mean this random thing. Here I mean this random quantity. Okay, oftentimes we mean this random quantity. It's just a random function here evaluated at x. When I write it like this, I mean the entire random function. Okay, so it's just random number. This is like deterministic decision rule. Decision rule. F hat is like a random function. So I'm looking at all the points here. And when I write something like f hat and x, this is doubly random because there's randomness in this because of the training data, and also the coordinate is also random because this x is a test data point. So what we have here is roughly the setup at x1 up to x y1, and then x2, y2, dot, dot, dot. These are the training data, yn, and xy is a pair. These are all IID draws. Draws from P. Okay, so this collection is my training data, and this is my test data point. This is just one sample. It's just a random sample from the same distribution, but this is independent from the training. Okay, and then when I evaluate this function, usually we work with a fixed x, and at the end you plug in the random x here. Now this is doubly random, so randomness in dn and randomness in x, but these randomnesses are independent. Okay, so far so good. right? So this is random function dependent on the n, random number dependent on the n. This is a random number dependent on dn and x. Okay. Okay, so what we can do is like I can measure the distance of two functions by, let's say if I have a deterministic function, if I want to measure how close it is to f star, I can take the L2 norm, which is just integral of this with respect to, I'm putting mu here. Mu is the marginal distribution. The marginal distribution of x under P. Okay, what I mean is that if x and y are drawn from P, then x has distribution mu. Let's say here, this is the joint distribution. Actually, this is just, let's say imagine this was for x, but let's say this is x, this is y. The marginal would be project down on this axis. It would be like a Gaussian in that case. So we take the average with respect to this distribution. Okay, this I would write as L2. This is for any fixed like f and f star is deterministic. This is just L2 norm squared. This is like L2 of mu, but I'm going to drop it. Okay, this is the L2 space of functions. If you have seen it, if not, it's just that integral. This is like a norm. If I take the square root, it defines a norm on these functions. Okay, it's called the L2 norm. Now, if I apply it to f hat, okay, so I can say that this is a loss. If you've taken, no, this is not a loss actually. There's one more step. So now if I so this, everyone understands this, right? So I can rewrite now this like this. So the tricky part is I can rewrite the same thing as expectation under f of x minus f and f star. I can write it like that. It's exactly the same quantity. Because I'm taking the expectation with respect to the distribution of x. This is my test point, right? So if you unpack this, it's just this guy, right? So that's another way of writing our sort of loss function here. Okay, so this I let this be my loss function. So this is the loss that we have. So this measures how well we're doing. Now, if I apply this to f hat n, this is a random function of my estimate dependent on the n. This is going to be a random quantity. And what I'm going to do is, I can say, for example, that this converges to 0 in probability. That's valid because it's a random variable now. Or I can say the expectation goes to 0. The expectation of this, if you want, in the language of 200B or decision theory, the expectation, this is called the risk. Okay. Then I take the expectation. This expectation is under the randomness of f hat n, under the dn, because the only randomness remains here is that. So this is now a deterministic quantity. And I can say this goes to 0. And the confusing part might be that this f hat n that appears here, this is as a decision rule. Okay, so this is not random. This quantity is not random. This is saying for this particular decision rule, this is the risk. The one that appears here is just that random function I mentioned. This is the decision rule, like you can rename it like something else. So the decision rule, like the decision, the partitioning estimator. This is going to be the risk of the partitioning estimator. This is the value, like the random function. You measure it against this, and so this is what we want to show. And if you unpack this, this is like expectation with respect to the n of L f hat and f star. But the other one, I can write it as like expectation with respect to x of f of x minus x star x, right, from the top. I'm putting x here to denote expectation with respect to this variable. I'm like when I put it here, I'm taking the integration basically with respect to this random variable. So if you unpack this, the outer expectation is with respect to the dn, the inner expectation with respect to x, and then the Fubini like tells you that this is also expectation over every randomness that you have. I can just write this. I can also write it like that if you want. Okay, so this is the simple thing. This takes the average over all the randomness in this because of the training, and the randomness in x because of the x. So these are all the composition of the error. Whatever you want, that's the meaning. All of these expressions are the same, and this is the meaning of this thing. So this is the one that I have here is just this version, right? But you can unpack it and say it's just we're saying basically that this is going to 0. They're all the same quantity. Okay, so to summarize, it's like this is also equal. We want the same expectation of x at a test point. So this is average over both the test and the train. And it's not something very deep, but it's just a little bit confusing maybe, but because confusion occurs because we're going to rewrite it in a different fashion again by conditioning. But I just want to point out that this is like an average. So this is averaged out over all the training. Sometimes you care about the individual version, but even the thing is that inside this, we have an expectation implicit, right? So you have an expectation. And so it's like double average over all the training and all the tests. You might want to say, I don't want to average over all the tests. What is like the exact, can I say that this goes to 0 for the majority of x's, like maybe that's not what you're doing here. This outer expectation going to 0 in this, it's fine because by Markov theorem, and this is converging in probability as well. So if the expectation goes to 0, you can say RF hat n. If this goes to 0, then you can say that LF hat n F star converges in probability to 0. Markov theorem. So this is a stronger, this is like the expectation going to 0. This is saying that, so this is saying that. Okay, so just maybe I'll post the notes that I have. They have some more details. Like just get comfortable a little bit with this notation. Okay, and then next time we come back and we can prove the stone. Hopefully, start proving it. And just one more slide. Here, the result that we get for the partitioning estimator. So those two basically technical conditions that I mentioned, this one, the key, and this, they translate into these two statements. Let's say for any ball or for any set, I'm gonna like the idea is that I'm gonna have a big set that covers a lot of these partitions. I don't want to like talk about all the partitions. Pick any B big enough, and then let the set be the set of all the partitions that intersect with B. All the, let's say the let's say I'll put a big ball here around 0, and all the pieces of the partition that are inside here or intersect with this. That's the all the cell indices that are there. I want the diameter of the cells there, the maximum diameter, go to 0. The size we want to shrink, that controls the bias, as we talked about. And also the total number, we don't want total number to be too close to n. So the total number of the cells divided by n, we want it to go to 0. This controls the variance, right? So it guarantees that we have enough points. So it's very natural, and this follows from the Stone's theorem. Okay, and next time we'll come back and talk about this. Okay, so these two very simple conditions, as long as your cells basically, this one you can say all the cells going to 0, the diameter, and also within any like bounded set, you don't want the total number to be close to n. To go to total number of cells should be like of the lower order than n. So it has to be like, for example, if you have constant number of cells, this definitely goes to 0, but then you'd have problem with this. So in order to have like the diameter goes to 0, I have to increase the number, but then I also have to worry. So these two are in conflict. Oh yeah, so these are the members of the cells of the partition. So as J varies, this just enumerates all the cells. You can ignore the n, it's just, yeah. Sounds good? Okay, next time we'll come back. Let's stop here, come back and try to prove that stuff.